progressing in our studies of the power devices that we can find on the market and basic topologies, technologies that we can use, we are now moving to the unipolar side. Up to now, the devices were all bipolars. PIN diode, bipolar junction transistor, thyristor in its two variants that are the SCR and the GTO. Bipolar devices have higher current capability usually. They heavily depend on the conductivity modulation. This means that the resistance is not the basic resistance of the silicon, but it is the resistance that you see when a huge amount of carriers is injected into the drift layer. For this motivation, bipolar devices also have problems in switching, because all this charge needs to be injected and removed from the device. Unipolar devices do not have this problem. The Power MOS is the first one that we study, let's say almost the only one that is completely unipolar, a completely unipolar device. The Schottky diode is another unipolar device. We are now dealing with the Power MOSFET. Everybody knows and studied the low power device MOS, very largely used in digital electronics, but also in analog circuits. You know the characteristics, you know the structure, you studied the layout, a number of things. Now we want a device that is a Power MOS, a MOSFET that is able to handle high current, withstand high voltage, reverse or forward blocking voltage, and that is able to sustain and manage a large power. Does this change its structure? Yes, it does. This is the conventional MOSFET that you know, let's say signal MOSFET, low power MOSFET. The device is manufactured on the top surface of the silicon. You have the wafer, and you have a diffusion. This is the substrate. You have a diffusion source drain. Both of them are on the surface of the chip, and the current flow is horizontal. Let's say it just exploits the surface of the chip, just the top portion. The substrate is there for mechanical purposes. It does influence the characteristics, but does not collect any current. Important parameters of this structure are the gate length, that is the distance between source and drain, and gate width. The width is important because it determines the amount of current that can flow. In order to increment the current, you need to increment this width. The main drawback in this structure, when you want to use it for high currents and high voltages, is that first of all the current is not flowing into the volume of the chip. You are not exploiting the entire silicon, but only the surface. This is different from what we have seen for PIN diode, bipolar junction transistor, GTOs. In all those cases, the current was flowing from the top to the bottom. This is the more conventional. This is the normal operation for a power device, because you exploit more thoroughly the silicon volume that you have. The only way to increase the device current is increasing the width. This is actually increasing the area, but if the current was flowing from the top to the bottom, you could increase the current by simply increasing the silicon area. Another very important motivation is that the drain voltage is limited. The blocking capability of this device is very small. because here these two junctions, and actually if you bias this terminal here, there is a depletion layer building up here, and when this depletion reaches the source, you have the breakdown, the point reach through, and you don't sustain any current. This means that the channel length determines the voltage capability. But you cannot increase the channel length too much because this will reduce the current. Breakdown voltage for this kind of device is no more than few tens of volts, very small voltage. This basic structure that you know is changed if we go for a high power device and becomes the structure that we'll see in the following slides. The relations that determine the behavior of this MOSFET are very well known. We recall them for clarity of notation. An important parameter is the threshold voltage. We will indicate this threshold voltage as VT. Sometimes you find this as VTH in order not to confuse this with the thermal voltage. But since we are talking about MOSFET here, there is no possibility of confusion. The threshold voltage is a function of the gate and source and substrate materials and silicon doping and the amount of charge that there is in the oxide and on the silicon. This can be designed. The threshold voltage is an increasing function of oxide thickness through the oxide, the capacitance of the oxide, and of for the NMOS of the body doping, because both Phi-star and QSC increase their joint behavior is increasing with the doping. When the gate to source voltage is larger than the threshold voltage, there is a channel formed under the gate, and there is a drain current that can flow. We are in the triode, linear or pinch-off regions. The dependence on the drain voltage in the triode region is this one. The current will be 1/2 mu n. This is the mobility of the electrons. Cox is the capacitance of the oxide. This is the channel width, and this is the channel length. And this is multiplied by twice VGS minus VT multiplied by the drain to source voltage minus the square of the drain to source voltage. This can also be written as K multiplied by the voltages in the square brackets, where K is 1/2 mu n C oxide double V divided by L. This is valid in the triode or linear region. When you are above the pinch-off region, that is, the drain to source voltage is larger than the gate to source minus the threshold voltage. The current is constant in the level 0 basic model of the device and is proportional to the square of VGS minus VT. This is the typical set of IV curves for low power MOS. In this case, we assume a threshold voltage of 1 volt. Kn for the NMOS is 50 10 to minus 5 amps divided volt square. The channel ratio is 1. In order to have the current that we see is few milliamps in pinch-off. If we are in the on state, let's say in the triode region here, the current is even smaller. These are typical values for digital electronics device. If we want to increase the output current and we want amps or tens of amps, the channel width must be 10 to 4 times larger. This is done actually also in high power devices simply by putting many elementary MOS in parallel. This means that the MOSFETs for high currents are usually composed of many elementary cells connected together on the silicon chip. And this is similar to the bipolar junction transistor that we have seen before. We will work in the off state and in the on state here. In the on state, it is possible to neglect the parabolic dependence of this characteristic here and get a linear model, a linear region for the MOSFET, getting an on-state resistance that is the ratio of the voltage VDS divided by the current. Using this equation and neglecting the VDS square, you get this equation for the on-state resistance. In this relation, you see that in order to reduce the resistance, you need to increase W. It seems that we can also simply increase VGS minus VT, but this is not possible over a certain value because the oxide has a limited voltage capability. And also because when the VGS is much larger than VT, there is a reduction of the mobility. There is a saturation of the mobility, reduction of the mobility, and this means that in the end, you cannot reduce the on-state resistance by simply increasing VGS. We can then increase the current, putting many devices in parallel, but still we have the very large limitation that says that the drain voltage is limited by the channel length that we want very small to very few volts. How to overcome this problem? How to increase the voltage capability? We need to move from the low power MOS device to this Power MOS structure. The first difference that we see, this is the structure. We have the gate on the top, the source on the top, N plus regions on the top. The drain is on the bottom of the device. In this way, first of all, the current flow will be vertical. We'll move from the source. Here, actually, there are two elementary cells in parallel. The current will flow in this direction, where these dashed green lines are indicated. There is a problem with the body. We are used to see the MOSFET with the source and drain immersed in the substrate, that is the body. Where is the substrate here? The substrate is the P region. The P region is here. This is the body of our MOSFET. And here is where the channel is formed. The body is now just diffused on top of the chip. And the substrate contact that here is at the bottom of the device now is on the top. It is here. And actually the source metallization, this gray line here, connects both the source and the substrate. In this way, the source to substrate voltage is always 0. We know that in order the source to substrate voltage has an influence on the threshold voltage. In this case, it is always 0. Thanks to this structure with the drain on the bottom, it is possible to introduce between the body region and the N plus drain a very large, low-doped, thick layer That is the usual drift layer, epilayer structure that we see for the power devices. This is the region that will help increasing the voltage capability of the device. This structure is not that difficult to understand. The difference, if you look at just half of this structure, we are actually simply taking this drain, moving it at the bottom, and getting a device that is with the source on the top and the drain on the bottom. The ohmic conduction between the drain and the channel is guaranteed by the fact that the drain is very wide. The drain starts from here, but it is also here. We will say that this region here is actually the intrinsic drain. The current can flow when the channel is formed here. The current flows, these electrons flow from the source through the channel and to the drain. This is the half cell, the elementary cell. Again, the current flow from the source to the drain. This is our intrinsic drain. Please note that the current is just electron current. There are no holes. There is no junction. There is no P plus N junction that is forward biased that can inject holes into the device. Hence, only majority carriers are responsible for the current. This is why this device is a unipolar device. There are no minority carriers and there is no storage of carriers into the device. From the manufacturing point of view, the body, you start with a substrate that is N+. The N- region is grown with possibly an epitaxial process. Then there is a first diffusion of P dopant to manufacture the body, the substrate. And then a second diffusion with higher doping to create the source region. Some space needs to remain here. In this two-dimensional plot, there is some space directly in the horizontal direction. And this space is needed to contact the body. In a three-dimensional structure, actually, we can have the source that extends up to here. And in the third dimension, you get one hole, one position in which you don't have the source. And you have the body contact. It is also possible. These structures are three-dimensional. You need to watch in the other direction. But doesn't change much the structure, the understanding of the device. On the top surface, there will be the gate oxide manufactured, then a polysilicon gate. The polysilicon gate here, it looks like there is no contact on the gate. Actually, also this one is contacted in the third dimension. If you imagine the third dimension of this device, at a certain point there will be a vias, a hole in the oxide that contacts the polysilicon gate. Another important aspect is that the channel is here, from this point to this point. It looks like the gate is only needed here. Why extending the gate up to the end of the intrinsic drain? In this plot, I could say that the gate can be reduced, cutting the gate here. Actually, we will see in a few slides that this will help improving the voltage capability, and this means this also helps improving the on-state resistance. And this means that the gate is one single piece of polysilicon that contacts two adjacent cells. The drain is on the bottom of the chip. This is a metallization here. This is the simplest things to do. The real structure is made by many elementary cells in parallel. One single cell is able to carry few milliamps. In order to reach the tens of amps, various the current capabilities that we need, there are thousands of cells in parallel. This means that the real structure is more or less like this, with many cells in parallel. This can be 100, 200 lines, cells, 1000 cells. At the end of the silicon area, there will be floating rings, field plates to terminate the structure. It is important to put as many cells as possible in a given silicon area because you want to increase the current capability. Each channel is one injector of electrons. You want to have many channels in the same silicon area. And this means that you need to study techniques and technologies that help you manufacturing these devices in very closely packed fashion. The feature size are not that small. It's not like low power devices where the channel length is now 20 nanometers. Here you always need to withstand high voltages. This means that this channel is in the order of the micron. You don't need very fine technologies, but still you need to improve the compactness of the structure. This is the most basic layout that you can find. Actually, many other solutions have been proposed to improve the density of the device. In this structure, however, we can observe some important dimensions. A, that is probably the most important, is the elementary cell pitch, the distance between the width of the single elementary cell that contains two MOSFETs actually. Then we have the W, that is the cell width, that is the extension in the third dimension of the MOSFET. And finally, we see that there is L, that is the channel length. Please note that now the channel length is this region, but still the drain is very far away from the source. This means that we are decoupling the current capability from the voltage capability. If we indicate as n the number of elementary cells in the chip, the total chip area is simply n multiplied by A multiplied by W. The total drain current in pinch-off is twice n times the current of each MOSFET, that is Kn multiplied by W divided by L multiplied by VGS minus VT square, where VGS is the gate voltage.